Your FastMCP server is getting hammered with too many requests, and you need to protect it from being overwhelmed, but you don't want to block legitimate users. We'll implement a sliding window rate limiter that tracks requests per client, automatically cleans up old entries, and enforces limits with precise timing. You'll see how to integrate this directly into the middleware pipeline with just a few lines of code. Import time. From collections, import defaultdict. From FastMCP server middleware, import middleware, middleware context. From MCP, import MCP error. From MCP, types import error data. Class simple rate limit middleware, middleware. Definite self requests per minute, int equals 60. Self requests per minute, requests per minute. Self client requests equals defaultdict, list. Async def on request, self context. Middleware context, call next. Current time equals time. Cliented equals default hash in practice. Extract from headers or context. Hash clean old requests and check limit. Cutoff time equals current time, 60. Self, client requests client ID equals. Rec time for rec time and self. Client requests client ID. If rec time, cutoff time. If len, self. Client requests client ID. Greater or equals self requests per minute. Raise MCP error data. Code equals 32,000, message equals. Rate limit exceeded. Self, client requests client ID. Append, current time. Return await call next, context. This demonstrates the intercepting filter pattern applied to request processing pipelines. The middleware architecture creates a chain of responsibility where each component can inspect, modify, or terminate requests before they reach the core handler. What makes this distinctive is its non-intrusive design. You add cross-cutting concerns like rate limiting without modifying existing business logic. The pattern works by wrapping the request flow in a series of composable layers. Each middleware receives the request context and a continuation function, deciding whether to proceed, modify the flow, or short-circuit with an error. This creates a clean separation between infrastructure concerns, like throttling, and domain logic, while maintaining a linear execution model that's easy to reason about. This approach solves the problem of scattered infrastructure code by centralizing concerns like security, monitoring, and rate limiting in reusable components. You deuse this pattern when building systems that need consistent policies across multiple endpoints, or when you want to keep core logic free from boilerplate. The trade-off is slightly increased complexity in debugging layered flows, but the modularity pays off as your system scales. Let's break it down. Import time. From collections, import defaultdict. This imports time for timestamp-based rate limiting and defaultdict to track client requests without manual initialization. The combination enables efficient request counting while eliminating key existence checks. Class simple rate limit middleware. Definite self requests per minute, int equals 60. Self requests per minute, requests per minute. Self client requests equals defaultdict, list. This implements a rate limiting middleware using the defaultdict pattern for efficient per client tracking. The constructor initializes the request limit and creates a dictionary that automatically initializes new client entries as empty lists, eliminating key checking boilerplate. This sets up the core data structure for tracking request timestamps per client. Async def on request, self context. Middleware context, call next. Current time equals time. Cliented equals default hash in practice. Extract from headers or context. This is the middleware's request handler, triggered on every incoming call. Current time captures the exact moment for rate limiting calculations, while cliented identifies the request source
though here it's hard-coded as default for simplicity. In production, you'd extract this from authentication headers or the context.
Cutoff time equals current time, 60. Self, client requests client ID equals.
This implements a sliding window for rate limiting. By calculating cutoff time as 60 seconds ago, it filters out stale requests, ensuring only recent activity counts toward the limit. This prevents memory bloat from accumulating old timestamps while maintaining accurate rate enforcement.
If len self, client requests client ID, greater or equals self requests per minute. Raise MCP error data, code equals 32,000, message equals, rate limit exceeded.
This enforces the rate limit by checking if the current request count meets or exceeds the allowed threshold. When triggered, it raises an MCP error with a standard error code, immediately rejecting the request and preventing further processing. This is the critical enforcement point that makes the middleware actually block excessive requests.
Self, client requests client ID, append current time. Return await call next, context.
This records the current request timestamp and proceeds with the request chain. The append operation maintains the sliding window for rate limiting, while await call next delegates to the next middleware or final handler, ensuring the request continues processing after validation. Rate limiting pattern. This simple middleware demonstrates FastMCP's request throttling by tracking timestamps per client and enforcing a sliding window limit, using Python's defaultdict for efficient state management. The 60-second cutoff time creates a potential edge case where bursts at window boundaries may temporarily exceed the intended rate. Cleaning old timestamps before checking the limit ensures accurate counting without requiring separate cleanup processes.
The middleware that forgets its past perfectly remembers the present.